All right, so let's move on to the third lesson of our unit of polynomial functions. And we're going to continue to learn some different properties of our polynomial functions, in particular with how they look as a graph, okay? And we're going to be analyzing in a little bit more detail the factored form of a polynomial function. All right, and the reason being is because the factored form of a polynomial function is a lot easier to be able to draw the sketch of what the function might look like. So far all we've looked at is the standard form of a polynomial function, but we're going to start looking at the factored form of a polynomial function. We're not going to discuss how to go from standard to factored just yet. That'll be later on in this unit. Okay, but we'll just be analyzing some equations in factored form and then what their graphs look like. We're also going to, along the way, determine whether x-intercepts are of even or odd order. Okay, so one of the things that we have to be able to identify from the factored form equation is the x-intercepts. And we're going to look at what kind of x-intercepts they are. All right, are they x-intercepts that cross through the x-axis in a linear fashion, or do they touch and then turn back up or down? So we're going to look at how to identify what type of x-intercept exists just from looking at the factored form of the equation. And also we'll be looking at how to determine algebraically whether a function is what's called odd or even. So an odd polynomial function or an even polynomial function. There's a test that you do algebraically to identify that. So we'll get to those items. Let's start by recalling what the standard form of a quadratic equation is versus the factored form of a quadratic equation. All right, because we would have all covered that last year. So let's refresh our memories a little bit regarding that. So if you can remember that the standard form for a quadratic equation is in the following format. Okay, remember that the degree is 2, right? The highest degree is 2 for a quadratic. And you have these coefficients a, b, and c. A being multiplied to x squared, b being multiplied to x, and then just a value, a constant of c. When it gets factored, okay, by a process called factoring, right, you end up with an equation that looks like this. It's an equivalent equation, right? It's completely equivalent. Ooh. All right, but it's just another way of writing it. And this method actually of writing it in factored form gives us more information. All right, and we'll discuss that in a second. All right, so let's look at an example. So let's say with actual values. Let's say this equation here was x minus 5 times x plus 4. Let's just use that as an example, all right? Notice I didn't put an a value. I'm assuming that a equals 1, all right? Just to keep an easier example, that a equals 1. And then here, if we were to expand this out, right, doing first times the first, first times the second, second times the first, and second times the second, we would get the standard form of that equation. So we would get x squared. It would then be plus 4x minus 5x, which would be minus x. And then negative 5 times positive 4 is negative 20. That would be our equation, our equivalent equation to our factored form. All right, so that's just to refresh your memory. I'm not going to explain right now how to go from standard to factored form. Okay, just vice versa. It's pretty straightforward. You just expand out your brackets like we've done so many times before. All right, so the question then becomes, what's the major advantage of the factored form for a polynomial equation? So what is the major advantage? Well, the factored form provides us with something that the standard form equation does not. provides us with the ability to determine the x-intercepts. Okay, that's the whole purpose of factored form. That's the whole purpose. And if you look at standard form, the benefit of having it in standard form isn't much. The only thing that standard form provides us, which I won't go into too much detail, is the y-intercept. The y-intercept is always equal to your c value, okay? Because remember that for the y-intercept, you substitute 0 in for x, right? That's the point that's the x value that always goes with your y-intercept. So subbing in 0 for x into this equation here and here, right? All you'd be left with is negative 20 as your y-intercept. Okay, so just keep that in mind. So that's a small piece of important information, but even greater is the x-intercepts. Now I may refer to the x-intercepts as the x-intercepts, or I can refer to them as the roots or as the zeros. So you'll see that they're referred to that way in the textbook and various other resources that you find. They're just referred to in one of those three terms. All right, so we have the ability to find the x-intercepts, but how exactly can you do that? So let's take that equation up here and let's figure out, I mean, I can easily show you how to do it. It's very straightforward, but I want to show you the background of why you can do what we're about to do to determine the x-intercepts, right? Because I think that's important to understand. Okay, because I can just tell you, but I feel like it's better if you understand the background of it. So remember that for the x-intercepts, okay, what does your y value always have to be? 0. Y must be 0. Okay, so if we were to substitute 0 in for y, or f at x, same thing, and we were to substitute that into our equation, what does this equation say to you? All right, understanding what this equation says to you is important. It says that 0 equals x minus 5 times x plus 4. Okay, and what it's really saying is that what values of x make this equation true. And by true, I mean equal to 0, right? Because it's saying that the equation is equal to 0. Okay? So what value or values of x make this equation true? So we're able to do this now in factored form. We can actually figure out which x values will make this whole equation, or will make the equation equal 0, but will make left side equal right side, all right, which is 0, right? So if my left side is 0, how can I make my right side equal 0? What value or values can I substitute in for x to do that? Hopefully you see that if either one of these brackets, this one or this one, if either one of those is equal to 0, then the whole equation is equal to 0 because it's multiplication, right? So it's x minus 5. If that happens to equal 0, then the whole right side equals 0. So what value can we plug in for x right here that makes our equation equal to 0? Okay, if you guessed x equals 5, then you guessed correctly. If we were to substitute a 5 in for x, right? If we were to substitute in a 5, right? So 5 minus 5 and then 5 plus 4, we would get 0 times 9, which is 0. So left side equals right side when x equals 5. Are there any other x values that will make this equation equal 0? There is, okay, because there's two brackets there. What other value? hopefully you see that it's -4. If -4 was x, once again, let's test it out. -4 minus 5 and then -4 plus 4, we would get -9 times 0, which is 0. So therefore, left side equals right side when x equals -4. Okay, so that's a good refresher. But now that we understand why we can find the x-intercepts or how we can do that, there's an easier way to do this. Okay, so if you have f at x is equal to x minus 5 and then x plus 4 times x plus 4. So all you need to do is set your equation equal to 0. Okay, and now all you need to accomplish here is, I like to do this just with little arrows pointing in either direction, is set each bracket equal to 0 and then solve for that x value. And here's what I mean. So set this bracket of x minus 5, set it equal to 0, and then solve for x. Oops. Okay, so x equals positive 5. Then do the same thing here. X plus 4 equals 0. Bring the plus 4 over to the other side. It becomes x equals -4. And there you have it. You have your two x-intercepts, or your roots, or your zeros. Okay? So that is how you are able to find the x-intercepts. We cannot do this using standard form. Like if I were to try to find the x-intercepts using standard form, right? So let's say this was my equation, like the one above, and I substituted 0 for y. Because there's no factors here, right? It's just an equation in standard form. How on earth would you solve for x? Because we have an x squared, we have an x. There's no way in algebra to solve that as it is right there, okay? So it's important that we have the equation in factored form, because factored form allows us this roundabout way of finding the x-intercepts by saying, okay, I can make my right side equal to 0 easily. I suppose you can still do it with this and kind of guess a bunch of x values, but it's much easier to look at it in this format and guess which x values, as opposed to this format and guess which x values will make this equation equal 0. Okay? So let's get back, or let's begin our actual lesson, where we're going to be accomplishing the following. Okay, determining x-intercepts from factored form of a polynomial function, determining the type of x-intercept, okay, odd versus even order. So I already discussed this, okay? So we're going to be looking at linear, quadratic, cubic, and quartic functions again. Determining the maximum number of x-intercepts for cubic and quartic functions specifically, and then determining odd versus even functions. Okay, so we'll accomplish those 4 items. All right, so let's begin. Examples of a factored form. Okay, examples of a factored form of a polynomial function. All right, so what is the degree of each equation below? We're going to be considering these 3 questions for all of these examples. What is the degree of each equation below? How can we determine the x-intercepts for each? And how many x-intercepts are possible for an odd degree function or an even degree? Okay, so let's consider this. Looking at this equation, how can we know what the degree of this function is? All right, because we need to figure out the degree. How do we know what the degree of the function is? Do we know of any way to determine that? Okay, well, there is a way to determine it, but there's a much faster way, which I'll show you in a second. But the way to determine it is simply expand this out, okay, and see what the highest degree is after you've expanded it out, right? See if you end up with an x to the 4 or an x cubed somewhere. Whatever your highest degree is, that's the degree of the equation, okay? Now, you can expand that out and that takes a lot of time, but there's a much faster way. Much faster way. And here's what you do. And actually, I'll erase this right here. Okay, what you do is you look at what each of the exponents are on these factors or these brackets. All right, what are your exponents? Well, in our case here, our exponents are 1 for each. And all you do to determine the degree, and actually I'll write that up here. To determine the degree, add all exponents of the given factors or brackets, right? That's all you do. So if we were to expand this out, this first equation, you would find that we would have a term that has an x cubed in it if we were to expand this out. And all you need to do, so it's a degree 3. And all you need to do is add 1 plus 1 plus 1, because those are your exponents, and you get degree 3. Okay, so just add the exponents. It's a shortcut. Number 2, let's see if we can find the x-intercepts. Okay, what values of x will make the whole equation equal 0? Okay, well, in this case, if x were positive 2, it would equal 0. The whole equation would equal 0. If x equaled negative 3, the whole equation would equal negative 0. And if x equaled 5, the whole equation would equal negative 0. So my x-intercepts are at 2, or let's start with the negative, negative 3, 2, 5. So it's going from smallest to largest. Okay, so how many x-intercepts are possible for an odd degree function or an even degree function? Okay, so let's analyze that here. Okay, I'm going to just do that below. I'm going to draw a graph. So that's a cubic function that we have above, a degree 3 function. Okay, let's analyze the most number of x-intercepts that you can have. Okay, let's check it out. So if I had a positive cubic function that did something like this, I can have 1, 2, 3. Okay, so in that situation, I could have 3. Is there any other way that I can draw this function? Well, it doesn't have to cross the x-axis in 2 of those locations. It could do something like this. So it can go like this, in which case there's only 1 x-intercept. Right? Is it possible to just have 2? Is it possible to have 2? Let's see. How can we draw this to see if we have 2 x-intercepts? How about this situation, where it touches right at that point and then turns back around? This would have 2 x-intercepts. And there's no other, there's different ways you can draw those graphs, but there's no other possibilities. You can either have 3, 2, or 1 x-intercepts. Okay, so for an odd degree function, okay, in this case we have an odd degree function. How many can we have? Okay, we can have a total maximum, actually, let's say, a maximum of 3. Okay, but we know that you can also have 2 and 1 as well. Okay, but let's say a maximum of 3. Now, if I go back and I use this space here to draw an even degree function, let's see how much is possible for that. By the way, there's a max of 3 x-intercepts for this particular equation because it's a degree 3. How many x-intercepts do you think would exist on a degree 5 equation or a degree 7? You're right if you're guessing that the number always lines up with a degree. So the number of x-intercepts and the degree of the equation are related. But it's just the maximum number of x-intercepts because it's possible to have less, as we drew below. Okay, but let's look at some even degree examples. So let's say a degree of 4. All right, so a degree 4 equation. So let's do this. How many x-intercepts does that have? It is possible where it was not possible before with the odd degree function. It is possible with an even degree function to have 0 x-intercepts. Okay. What about, can you have 1 potentially? Okay, can you have 1? Let's see. Yes, you can certainly have 1. So that's 1 x-intercept. Okay, what else is possible? Can you have 2 x-intercepts? Definitely, you can have 2. Okay, and running a little bit out of space there. Can we have 3? Let's see if we can draw, and then I'll just erase these after. Can we have 3 x-intercepts? We can, right? 1, 2, and 3. And then lastly, can we have 4 x-intercepts? Definitely, right? 1, 2, 3, and then 4. So if we were to conclude here, I'm going to erase these graphs now and we'll write a conclusion there. Okay, so I just wanted to use this space to explain this to you. But we can actually, for an even degree function, you can also have 0 x-intercepts. And that makes sense because the end behaviors are doing the same thing. They're going in the same direction. Whereas for an odd degree function, they're going in opposite directions, right? So it's like the end behaviors is doing something like this, where at some point, one of those two ends of the line will cross your x-axis. It has to, okay? But when it comes to an even degree function, because the end behaviors are the same and they're going in the same direction, you actually don't have to have any x-intercepts, right? So I want to write a conclusion to that. Let's erase okay. So number of x-intercepts. So for an odd degree function, okay, you can have a maximum of n, where n is the degree of the function. Okay, so if it's like a 5th degree function, you can have a maximum of 5 x-intercepts. Okay, so that's for an odd degree, but can you have 0? No, you cannot. Okay, no, you cannot. Now, for an even degree, it's a little bit different. Okay, you can have a maximum, again, a maximum of n intercepts where n is the degree of the function. Okay. But this time we can have 0 intercepts, right? We just looked at y, we proved it, okay? So let's go back and let's answer the following. Okay, now that we have done and developed how many x-intercepts are possible. So number one, what is the degree of the equation? Well, remember, add the exponents of your factors, 2 and 1. Okay, so what is it? The degree is 3 again. Okay. Number 2, what are our x-intercepts? What are our x-intercepts? This time, how many x-intercepts do we have? Okay, let's take a look. So if I set that first bracket equal to 0, okay, if I set that first bracket equal to 0, let's see what happens. So if I do x minus 2 squared is equal to 0, okay, square root both sides, you get x minus 2 is 0, and then once again, you get x equals 2. Okay, so that's how you handle this little square thing. Don't be thrown off by that, right? Still set it equal to 0, but then move the square to the other side, so you square root on the other side, while the square root of 0 is still just 0, okay? And then all you're left with is x minus 2 on the left, and then add 2 on the right to bring it over, and you get x equals 2. For the other intercept, it's straightforward. Simply set it equal to 0, and it's x equals negative 3. Okay? Now, how many x-intercepts is that? Clearly, this has 2 x-intercepts, which is a possibility. It is a possibility, right? We said that it can be up to a maximum of the degree of the equation, so it could have up to a maximum of 3, but it can also have 2 or 1. But because it's an odd degree function, it cannot have 0 x-intercepts. Okay, next. This is once again a degree 3 equation. This is just another type. Okay. Set that equal to 0. Okay, so that means take the cubed root on both sides to get rid of that cubed here. Take the cubed root of 0, it's still just 0. So it's just x minus 2 equals 0. And then x equals 2. There's your x-intercept. Okay, remember, to bring the cubed over to the other side, you take the cubed root of 0, which is still just 0. Okay? And how many x-intercepts does it have? It clearly only has 1 x-intercept. Okay, at 2. Okay. Let's move on and let's look at the types of x-intercepts that are possible, because each one of these examples above has different types of x-intercepts. Okay? They have different types. And I'll try to explain. So let's say we have a degree, let's do a degree 3 equation. Okay, and I'll give you an example. Actually, let's start with degree 1. Okay, so an example would be something like f at x or y equals x plus 2. Why is it a degree 1 equation? Well, it's in y equals mx plus b form, and the exponent there is a 1. So it is a 1. Okay. X-intercept, x equal to negative 2, will make y equal 0. So my x-intercept is negative 2. And the characteristic of how that looks, okay, the characteristic of how that looks is, remember, it's just a straight line, and the intercept is at negative 2. Okay, right there, negative 2. So what is that? It simply just crosses the x-axis, crosses through x-axis. Okay? So, I mean, that only has one example there, but let's look at 2. All right, let's look at 2. So what if we have a degree 2 that looks like this? Okay, that's a degree 2 equation. What is our x-intercept? Again, it's -2. But look at the difference now. Okay, when we have a degree 2 on a on the outside of our brackets, okay, remember that this only means that there's one x-intercept. So how do I draw one x-intercept at x equals -2? Well, it's going to be the vertex of our parabola. It's only going to touch the x-axis and then turn back in the other direction. Okay, so this touches x-axis, but never crosses. Okay, what about a third degree? A third degree. Okay, how does that look exactly? So if we had an equation that looked like this. Now remember, there's all different kinds of third degree equations. For example, like all of these were third degree equations, and we'll come back to this in a second. Okay, so let's say, I don't know, I have x, this time x plus 2 to the power of 3. So it's a cubic or a third degree equation. My x-intercept is still -2, but you draw that differently because of the cubed. You actually draw the intercept there differently. Okay, so here's what you do. You go like this. You know how the cubic function kind of does that little weird thing in the middle, okay, where it either kind of turns directions. Okay, well, instead of turning directions, it actually goes through our x-axis, still at -2, okay, but it does so through a point at -2 and then continues in the up direction. So instead of doing something like this, it's doing something like this. Okay? All right, so the characteristic of this, I would say that this does cross through the x-axis. Okay, but it does so in this kind of different way, different than linear, right? Linear goes directly right through it. This kind of slows up, then goes through it, and then speeds back up again. Okay? And now lastly, if we have a fourth degree equation, so we have something like this to the power of 4. My x-intercept is still at -2. Okay? But I have it's going to look like the parabola, but it's actually going to be like a wider, it's still going to just touch at one point, but a fourth degree equation, a quartic function, is just a wider version of a parabola. Okay, so it kind of goes a little bit flat right here, but it still only touches the point at -2 and then turns back in the other direction. So just like here, it touches the x-axis. It just does it in a wider, it looks like it's wider than the parabola. It touches the x-axis, but never crosses as well. Right? But we know that these aren't the only versions of these. Like I can write a quadratic equation. Instead of it being like this, for example, I can write a quadratic equation that looks like this, where there are 2 x-intercepts, right? Whereas this one, there was only 1 x-intercept, so it had to be that turning point. Well, you can also write it as 2 x-intercepts, where it's not the turning point, okay? Where it's not the turning point, it actually does something like this, right? And it has 2 x-intercepts. And the way you know how it crosses the x-axis is you look at the degree of each factor. If the degree is 1, then it's going to cross the x-axis just like a degree 1 equation does. If the degree is 2, Okay, so let's say we have a cubic function that looks like this. So there's a squared here and then to the power of 1 here. That's a cubic function. Okay. That means that at -2, it is going to have one x-intercept. So it's going to look like this. It's going to touch once and then turn back around. And then at +1, it's actually going to go through the x-axis. Okay? So because of the squared there, it only touches the x-axis and then turns back around. And when there's a 1, it actually goes through the x-axis. So that's super important in helping us draw the sketch of different graphs if we're given the factored form of the equation. Okay, that is going to be super helpful to us. Okay, last thing that we're going to do as part of this lesson is determining odd versus even functions. Okay, some polynomial functions are symmetrical across the y-axis. These functions are what is known by even functions. It can be determined by completing the following check. So, some polynomial functions are symmetrical across the y-axis, just like this one. See across the y-axis how there's symmetry on both ends, both sides? There's a way to check that. The way to check it is using this algebraic method of testing. If we substitute a -x into our equation wherever we see x, and it ends up equaling the original function still, then it's considered an even function. So here's what I mean. Okay, so here's our function. Right? Because to actually understand that, you have to look at an example. Here's our function. If I now replace all my x's with -x, like it says here in this rule. Okay, so if I replace all my x's with -x, I substitute -x here, will I get the same equation as was given to me from the start? That's what this is stating. If I substitute -x, will I get the same equation? So let's see. If I put in a -x, let's see if I get the same thing as this. So I go -x to the power of 4 minus -x squared plus 2. Let's see. Well, a negative number to the power of an even exponent, 2, 4, 6, 8, 10, will always become positive. So even though it says -x to the power of 4, because it's to the power of 4, it's just going to be a positive number. It'll just be x to the power of 4. Okay? Then minus, and same thing as before, a negative number squared will end up just being that positive number. So it'll just be x squared. And then plus 2. And lo and behold, you see that they equal each other. Right? They equal each other. So you would write, therefore, f at -x equals f at x, okay, and is an even function. So that means that there is symmetry across the y-axis. Okay? So that's how we check that. What about odd functions? All right, so you can have odd functions. So we've got to get all this clear in our heads now because there's a lot of different things here. Okay, we can have what's called an odd or even degree equation, which has to do with the highest exponent that exists in the equation. We can also have an odd or even order x-intercept type. Okay. And if it's an odd order x-intercept type, that means it goes right through the x-axis. If it's an even order x-intercept type, that means it touches the x-axis and then turns back around, but never goes through it. And now we're doing odd and even functions. So there's 3 different things we need to get kind of straightened out in our mind. Okay, and over the next couple of days, we'll make sure that we can do that. But let's now determine an odd function. So some polynomial functions are rotationally symmetrical around the origin, also known as point symmetry. So rotationally symmetrical, and actually this should be drawn down here, around the origin. Okay, so it should be here. Okay, so if I were to rotate this this curve, if I were to rotate it, we would get the exact same curve if I rotate it, let's say 90 degrees. Okay, so every 90 degrees that I rotate it, you'll get the same curve. So the way you check that, if it has what's called point symmetry, okay, is you find f at negative x, so you substitute negative x into your equation, and then you also find f at x times negative 1. That's what that means there. Negative f of x means f at x times negative 1. If those two equations end up being equal, then we have what's called an odd function. Now, this particular function, we can just look that it doesn't have point symmetry around the origin. It does have point symmetry, but just not around the origin. So just by looking at the graph, I know that this is not going to be an odd function, but let's double check it. Okay, let's double check. Okay, so let's find f of negative x. All right, so let's do take all my x's and replace them with negative x. Okay, notice that the minus sign here, don't get confused there, the minus sign I brought down, and then I still had minus negative x. So what do I get? Well, negative x cubed, a negative number cubed, is actually still going to be a negative number. Okay, it's not like to the power of 2 or 4 or 6 where it becomes positive. Any negative number cubed will remain negative. Okay, and then minus a negative x would become plus x plus 2. Okay, so that is our f at negative x. Let's compare that now to negative f at x. Okay, which means just take our original equation of x cubed minus x plus 2 and multiply it by negative 1. So distribute the negative 1. You get negative x cubed plus x. Ooh, so close, right? But then negative 1 times positive 2 is negative 2. So take a look. Are these equations the same? Almost, right? And that's why it almost has symmetry at its origin. It does have point symmetry, just not at its origin, right? So it's very, very close. But our conclusion would be that f of negative x does not equal negative f at x and is not an even function. It's also not it's not an odd function. Sorry about that. It's also not an even function. Okay, but it is, the question is it odd or even or neither? It is neither, right? So if f at negative x equals negative f at x, or does not equal negative f at x, then we definitely do not have an odd function, okay? But is it an even function? Well, let's see. Is f at negative x equal to f at x? Because that's our test if it's an even function. So our f at negative x was this. Does it equal our original equation? No. So it also is not equal to f at x, and is also not an even function. Okay, so it would be neither. All right, so we tested that equation out. We tested if it was an odd function. I did a quick test. Once I did the odd function, it was easy for me to do the even one because I already had f at negative x right here, because we already found it up there. And then I just compared it to my original. And so it's pretty easy to tell that it wasn't an even function. So it must be neither. So it does not have symmetry across the y-axis, and it does not have point symmetry at its origin. Has neither. Okay. All right, so summary of odd versus even degree. Okay, so odd versus even degree. Let's summarize this quick. So an odd degree equation has opposite end behaviors, right? Opposite end behaviors. Whereas an even degree equation has identical end behaviors. Or let's not use the word identical. These same end behaviors. So meaning that we would have something like this versus something like that. Okay? So the arrow's going in opposite direction versus the arrow's pointing in the same direction. Okay, what about odd versus even order intercept? Okay, so let's look at this. Let's look. If I have an intercept that goes right through the x-axis like this, or, and actually let's do, just like we did above, let's go odd versus even. So if we have something that goes like this, right through the x-axis, it's considered an odd degree x-intercept, or sorry, an odd order x-intercept. Or it can do something like this, where it was like a degree of 3. It's still odd, but it does something like this. That is still considered an odd order intercept. This is a first order. This is a third order. For even, you can have this. Okay, this is a what's called a second order intercept. Versus a wider fourth order, so it can be something like this. This would be considered a fourth order intercept. Okay? So we're going to be doing some questions, and I'll do a sample question with you on how we're really going to analyze this part of it, right? So we're really going to get more practice with that. But let's touch base on just odd versus even functions. Okay, that one is actually just takes a little bit of algebra. So for an odd function, if f at negative x, so substituting negative x into your original equation, is equal to taking f at x and multiplying it by -1, okay, the entire equation. If that's true, then you have an odd function. If f at negative x is just equal to f at x, then you have what's known as an even function, meaning symmetry across the y-axis. Okay. Now, I would like to do an example with you that really dives into this here. Okay, so let's do that really quick. I'm going to ask you to draw a sketch of the following. We're going to tie everything together here. Okay, if I have an equation, f of x is equal to x minus 2, x plus 4 squared times x minus 7. Okay. I want us to be able to draw the sketch of that. Okay, so what information do we need to extract here in order to draw the sketch? Well, for one thing, what is the degree of our equation? I mean, we need to know that, right? We got to know the end behaviors. It's a degree 4. Okay? Okay, good. Degree 4. Now, it'd be also a good idea to determine my x-intercepts, right? So I can kind of just roughly plot them. Well, my x-intercepts are x equals 2, x equals -4, and x equals 7. Okay, so -4, 2, 7. So I have 3 x-intercepts here. 3 x-intercepts. I also need to know, is my graph opening up or down? Okay, up/down. Well, how do we determine that? How do we determine? Or let's use the term direction there. How do we determine that? Well, it's your leading coefficient. My leading coefficient here is +1, is my leading coefficient. So if my leading coefficient is +1, it must be opening upwards if it's a degree 4 equation. Okay? And now I think we're ready to do a rough sketch here. Okay, so let's go -4, -2, 0, 2. Let's draw them a little closer. Okay, so let's see here. I have got a graph that's opening up. It's going to cross x equals 2. It's going to cross here in what type of fashion? What type of intercept is this? If there's a 1 here, is it it's a first degree intercept, which means it's going to cross through the x-axis. So for this one here, it will cross through. Okay? But look at for x equals -4. So I'm definitely going to cross through here at 2. Look at -4 though. It's a second order intercept, which means that it will cross through. It won't actually cross through. It will touch, but not cross. Okay, so it will touch but not cross. And once you have that one, the last one at 7, so let's say that's 6 and then 7 would be somewhere there. 7 will cross through. Okay, so it's going to cross through. So at 2, let's draw this. At 2, it's going to cross through. -4, it touches but does not cross. So it's going to look like this. Okay, everybody? It's going to be pointing up. So we're going to start in this direction there. It's going to touch -4, turn back. Okay? And then it's going to cross through 2. And then it's going to cross through 7. It's going to look something along those lines. All right, try to draw it as a smooth curve as best as you can. So it's going to look something along those lines, okay? So it's going to be pointing upwards, okay? Touch at -4, turn back around, then cross through 2, and then cross through 7. All right? We're going to practice this over and over again because this is really what we need to take from the first 3 lessons so far, is something like this. Okay, so we're going to be practicing this over and over. So if you're struggling with it now, repetition and doing as many questions as possible will be very helpful. Okay.